let's see. Let's try and work through the syntax and implement something. I took some notes here somewhere. Let's do a function on vectors. Okay. I think a nice one is from 2. Okay. Or replicate. Let's go with replicate. But we're gonna make it from scratch. We're not gonna look it up. So where's the shit? All right. Okay. Okay. So wait. Cd test. Oops. Okay. And okay, let's see, vector LP. So I'm gonna try and define the vector function, and I suppose first let's see. Let from to equal. And first we're using the, so we want to do, so this function is going to give us a range of numbers. So if we give it, a number, it's going to give us the range from 0 to that number. And so we're going to start with a NAT eliminator. And first we need to give it the, let's see, yeah. First we're going to give it the, wait.
Maybe show the slide where you have the type of NAT element.
Good point, good point. Not ln. Typing of limiter. Okay, here we go. So first we need to give it the motive, which would be lambda n. Wait.
So motive is like the type you want, right?
Sorry, what?
Isn't like the type the motive?
Yes. Yeah, so we have a vector of NAT and n. So we take something, we take an n and we return vector not n. Should be correct. And then first question is, what is our
Sum of n? Well, suppose you give it 0.
Yeah.
Your resulting function, will it be an empty vector or will it be
Very good point.
The element 0?
Yes. Good noticing.
Okay.
So that'll be sec of n. And then let's see. Now we need to give it the 0 case.
I would say like the first one is underscore, right? And you just want
No?
I don't understand why it's suck of n, because the eliminator, the first thing that we are going to give is the type, right? So it's something that takes a natural and is going to give us some type, and so for 0 it's going to give a vector of NAT of length 0, right?
Yes. Wait. Yes.
What you want your function
That's a
to
good
do.
point.
So if we give this function from 2, if we give it the
What
number
is
0,
the
what do we want to return? Do we want an empty vector or do we want a vector with the element 0 in.
Good point. I guess.
We can choose probably.
Yeah. Any preference for you guys?
From 2 means that there are maybe 2 naturals from and to, which sounds too difficult.
let's start with something.
From 0 to.
Yeah.
Let's first. Can you say what we are doing?
Oh,
Right.
Yeah, so then it's n and m, and then it's like the vector of the natural is n minus n, right? Or n minus n, I would say.
Okay.
And minus
It's
m?
like, it's like the size of the range from that number to that number, right?
Yes.
Yeah, and then it's inclusive or exclusive.
That's
Let's say if we have 0, we should just get a vector of size 1 with the 0 in it. And if we and if we get
Then here you want suck.
yeah. Suck. And, yeah. So then we need the zeroth case. So let's just open some existing ones so we can look at the code.
Should be vector of size 1.
It's a little bit smaller because
Smaller?
the case
Oh.
now just falls.
Yes.
Yep.
Yes, exactly. So because there were handlers and it has
So lambda pi
but it needs to be a
prelude. So let's look at the vector case. And
then a block fetch client which actually is slightly different. It's a function we put here because we don't have the definition
from 2.
Okay.
Is that the one, right?
yes, here we go. So right.
So it's actually n is not
Yeah,
successor,
so I
right?
think it's
That gives sense.
Oh, okay. So it's actually that's what example was. It's actually not giving you. So n is 0. That was the confusion. So then.
and then there is a function
Okay.
which
So let's go back and then try and do this ourselves. So first we're giving it the base case. So if we have 0, then we return, we don't care about the argument, and we return the nil of type not. Should be in the bracket. And the second case, we take our thing and we recurse and we return the cons not successor, I think. Cons not successor not. Yeah, this gets, so the problem with that one is that you end up having to tell you, for data constructors, because we don't have implicits, we have to tell const that we're taking the net. And then we have the size of it, and then we need to give it the list that we are consing to. So in this case, that... Damn. I'm not used to working with that. So okay, yeah, here we have the actual thing, is that we have const not, and then we recurse. So we keep adding the further ones, and we just keep getting this like large expression until it gets to 0, and then we just have this large cons expression.
So the reason that it's not successor of n is because the cons is doing the +1 for you.
That's the point, yeah.
Yeah. Oh yes, yes. So,
We
but
already know n upfront, so we don't need to do it like a successor. Yeah.
Yeah, the end that you give to cons is the length of the factor that you give.
yes, yeah. So, and then once we recurse, it's going to keep increasing. So, yeah.
And we also like, that's the thing we do in the right, right? So we don't need a successor to that, and that either, so we should hold that on the other one as well. Like in itself. So we don't,
Yeah.
like before we didn't put in that successor, so we don't need it.
Yes, yeah. Right, true. And then, yes, you have the recursive case, and then you close it. Oh?
So now you put the primes.
Primes?
So you now wrote const nat n
Oh, yeah.
prime.
Yeah, very true.
So then you have to add one.
Oh yeah, good noticing. Yeah, because yeah, we're using n already, so we're using a different one. Right, let's run something. We shall.
In this case, because we say just the value, not the function, the next two things don't take, or at least the first one doesn't take an argument.
Okay. From 0 to. Ta-da! 0 to 10. Can do things like that. What else is nice to try? Oh yeah, I suppose maybe addition would be a nice thing to implement. Because if we see how to add two of them, then you'll see dependent types in action, which is quite nice. So let's go into vect LP, and let's say we want to do let append equals, and so our append we want to be adding to let's see.
Should we first write the type?
Yes. Or yes, I don't know. I think we're running out of time, so I'll just show you guys. It's a little bit too slow, I admit, doing these things from scratch. So the interesting thing with append is that what you're getting. So first you have your parameter for A, and you have the delimiter, and you have vector. So you take your m as an input, and you take your n of the other vector for input, and then the output type is vector A, and then plus mn, and the plus was the natural number function. So here essentially we're making this predicate and saying that there's a relationship between the values of the output type and the values of the two input types we got. And the output vector will always have this size. And what we have, okay, so you can see m underscore v. This just means that when we're getting this one, we don't need to care about the that part, because we're just defining the type. All we care about is the size of it, and then here for the 0 case, we don't care about the left-hand side, because if we're adding 0, then all we care about is the one of the values. We just return it. And the last case, this is the recursor case. So we recurse on the just like similar how you recursively add a list to another list, but in this case, what do you do with vectors? Yeah. Yes, there's a few. Oh yeah, another interesting one would be the map. So we can define map on the vectors as well. And we have the type of, so the important thing in the vector an goes to vector bn, and we get some type a, and we get some type b, and we get the function from a to b. And we still have the size. So in this case, again, it's kind of, yeah, straightforward. Right, and I guess the final thing to go through is a bit about equality. So this, we discussed it a bit yesterday about proving that certain things are equal. And normally this would be something you use when, okay, so an example would be if you have the type of, but the problem kind of that arises with these kind of type theories is that when you have, let's say, our plus function, as I mean the append. So here we have a predicate that the output list needs to have this relation to the input lists. The problem is that sometimes when you have these predicates, even though intuitively it's obvious to you, it's not obvious to the compiler. And I think, as I was mentioning yesterday, one example would be if you do plus 0 and then, and you prove that 0 and n is equal to n, and then you have the reverse case, and then 0, and the compiler complains, and it says that, oh, you need to prove this as well. And so, to prove that, you would use the equality type. So you would do something like, so you have type A, and you prove that the first argument is equal to the second argument. You prove that they're the same type. And that allows you to use that in your proof. So you're then able to make your expression type check. And your compiler doesn't complain. And in principle, you could equate, you can construct this type for okay, so to construct this type, you go for the ruffle. You go for this. And so yeah, and then to use it, you use the eliminator. And okay, I do apologize for how it looks. If you're using Idris or something or Ragda, then all this boils down to is just the pattern matching on it. But I guess, yeah, it looks a little bit daunting there. But essentially the idea is that if you want to construct your proof, then you put your, you construct the term using ruffle, and then you're able to use that proof using the eliminator in whatever place needs the proof. And yeah, we can quickly look at the implementation of it. And oops, where was that?
My expectation was that EQ should take like 2 times, yeah?
Yeah.
But it looks like it can, but it can take 2 values as well in this interpretation. Yeah.
Let's see. So for all A of type star and X is type A, and we give A, and then
so I can have A
Yes, yes. Or you can have A as type, and then X as whatever.
A is star, star and star, and then X is type,
Yeah, yeah. Some kind of type.
Wouldn't it be sufficient just to have EQ type like EQ star to star to star?
Star to star to star. But then we're trying to say that these two A's are equal. So we need to explicitly refer to them. If it's star to star to star, then we can put any random 3 stars there.
It depends whether we have a constructor for this type, which accepts distinct type variables. Even if type itself allows it, we can maybe there is no constructor or doesn't work this way.
Oh, I mean, so that's kind of, yeah. So we yeah, so yeah, so in another syntax, how this would be, like for example, in Idris, the syntax says, I think it's A to B to type A equals B. And so yeah, you could put in any 2 types there, even if they're not equal, and then you're simply unable to construct the REFL constructor for it. And that's kind of how you do it. You have your 2 things, and then the question is this type inhabited? Does this type have something in it? And if it does, then that's your proof, essentially. And for something like equal not to bool, they're not equal, so you can't prove that. And it's kind of, yeah, nonsense.
You only have one inhabitant this time. You only have one inhabitant this time.
Then that's also fine, yeah. I guess the classic type with 1 inhabitant is unit, which only has 1 thing inside of it.
And the REFL also have 1 type.
Oh, I see. Yes, yeah. But the REFL could have it's 1 data constructor, but the data constructor can have many different proofs of the same thing.
They're not the same.
Oh, I see. I see what you're saying.
Two booleans, if you compare 2 booleans and 2 integers, they're not the same. These 2 REFLs are not the same.
Sorry. Yeah.
They're the same. So I can construct the REFL.
Yeah.
And I can construct the REFL from the 2 integers.
Mm-hmm.
2 integer types. So
Yeah.
these 2 REFLs are there the same.
Oh, I see. No, that'd be different because you can't. So okay. No, that's actually a good question. So remember we discussed type families yesterday. In principle, you can think of it as a type family parameterized by a few arguments. So your actual type would be equal int. And then you have, the question is, yeah, do you have a REFL for that type with those applied? So you don't construct a REFL for like everything, you're just constructing it for 2 specific types. And then if they're equal, then it's inhabitant.
If you have a REFL for boolean and another REFL for the boolean there.
Then you can prove in there that boolean is equal.
Only if they are the same term. Only if they are the same term after elimination. So this instance is constructible only if these arguments after the elimination are the same term, right?
You need to simplify them. So because you can have arbitrary computations in your types, then they need to reach the normal. That's how we're doing it to intentional equality.
Okay. Yes, but this eliminator only converges to a term, the EQ eliminator, right? Only if the terms are equal, right?
Well, they have to be equal, and you have to prove that they're equal. So you have to give it something. Otherwise, if they're not equal, then you can't construct the REFL data constructor. So essentially,
So it's in the type, okay, I understand.
Yeah. Yes, essentially in here we do it this way, but it's also possible to do it in a more general way and kind of do it that way. So let's look at a few proofs. So here's a thing from logic called the Leibniz equation, which says that if you have two types and you have a function from one of these types to another, and then you have two values, and you can give me an equality that says that these two values of type A are equal. So you have this proof. Then you automatically gain a proof that those values with the function applied to them are also equal. So that's a nice equation. And let's see, what else is there? Oh wait, here's have symmetry of equality. So you can prove that if you have equal xy, it's the same as equal yx. So equality is symmetrical. Again, something very obvious to us, but need to say it explicitly to the compiler. And again, so as an input,
So how can they prove it? How this EQ eliminator works?
Yeah. Essentially, since you're dealing with an arbitrary type A, so you get lambda A, and then so we're taking lambda x and lambda y, and the proof of equality between x and y, and then we get the type equal a yx, and then we construct as a term on bottom ruffle a x, and the y in this case is implicit, so you get your ruffle axy, and as you can see, we've swapped them. So essentially, it's kind of like a formal symbol manipulation. You're just kind of seeing if you're allowed to do this manipulation, and then if you succeed, you've got it.
Why does the ruffle only get an x, not a y?
So the y argument is the because it's of the if it's the it's kind of like the problem with the eliminator approach is that you're explicitly talking about one it's basically implicit. It's like when you're dealing there, it's kind of like assumes that you're gonna have your thing there, and then it just applies it to that.
I guess this is because we already have a proof that y and x are of the same type A. I mean, the signature of EQLM seems to enforce that.
Yes. Oh, yes. It's a very good point. Yeah. So we are only having one value here ultimately. That's right. Yeah. Because you don't need two values of it, because by this point you know they're equal. So if you had a y, essentially you would just have axx, And if you're working like with Idris, then that one has a tactic which actually just kind of renames it for you in this case, and then equates them.
The idea of REFL is that it's a proof that x is equal to y, right?
Mm-hmm. Yeah.
How is it a proof when there's no y?
It's a proof because it.
It's like an
reflexivity. Everything is equal to itself.
Yeah, I get that x is equal to x, but we're supposed to be proving that x is equal to y, or y is
because
equal to
x can only be equal to x. That's the reflexivity. So you can construct the instance of ref only for if you can essentially prove that it's the same thing. That's why it doesn't have the other argument.
So EQ is a proof and REFL is just an evidence.
It's just an instance of data type that carries this proof, so to say. And it only is if you have proven that x is x, so to say. Because there is no other way to construct that instance. Had you been able to construct that for x and y, then you would have proven nothing, right? Because it would be arbitrarily x and y. Is that true?
Yes, yeah, exactly. If you couldn't construct it, then yeah, if you did this for something like
So the dependent constraint here is that x can only be x.
yes.
So is REFL AX a proof for X being an inhabitant of type A?
Or the is we have no it's the REFL itself. The fact that you've constructed this REFL which type checks with EQ, it's the proof that EQ has an inhabitant, which you've provided.
Okay, so it means that there is some notion of equality for values of type A, which X exemplifies. I mean, X exemplifies the value of that.
Yes, yeah.
So REFL is a way of obtaining the equality for the type of the value that I've got at hand, right?
Yes, and there's all yeah.
Is the only instance of type EQ, which
Type
is
EQ.
be constructed if both arguments of EQ are the same. Pass REFL doesn't need any other y apart from x. Or,
Can we match this usage of EQ eliminator with slides, please?
Okay. Let's see, which one would be a simple one to work with?
Well, this one looks like.
Okay, cool. Yeah. Right. So you have your EQ eliminator, and it needs to get the motive first.
It needs to get alpha first.
Oh yeah. So for all, but yeah, alpha is part of the motive. So but you can start there. So if you have EQ AXY and evaluates to star, in our case, the star is another EQ AYX. And then, yeah, for all A star, so there has to be a type. And then for all M of type, for all XA, for all YA, so these are two values, star. And then the first case, or the only case because only one data constructor, we have for all Z of type A, we have MZZ REFL AZ. So this would mean that
This is motive. Yeah? This is emotive.
yeah. And we get the motive, and we get the actual case for taking a value and constructing it. So essentially, okay, we're going to have, so the value of equal xy is going to be a raffle, right? And the evaluator for this equation strips away the initial raffle. And so we're left with the value of that raffle, which is the x. And the value we pass on to our output, but first we put the data constructor back and also the type. So essentially, x was the previous value which we already had as part of this type. And we're just putting this x into as a value of the output type.
So just to clarify that raffle, is that the base case of the induction? Like, so that's the like the base case would be like x is like its own reflexive value, right?
Yes, yeah.
That would be the base case, right? So if you take the next step, would be like the equality of x and y would be the same as the equality of y and x. Why is the two terms inverse on like the right side of the arrow? Or is it just
I think it's one of those cases where it's so simple that we're kind of it's hard to describe, because essentially it's the same value used in both equations, and you're just taking this value from the left one and putting in the right one, and it's still valid. Maybe if we, so if you look at the way the raffle is constructed using it in other ones, so you have equal axy to equal b fx of y. So we just need to, again, we have take the same inputs, xy, and proof of equality. And then it takes some value. And we apply it here. And then f applied to that value is going to have type B. And we have type B given here. Again, we only need one of them here because
well, it's because of the type checker.
Yeah.
So raffle, if you ignore the B, raffle something fx is a proof that fx is equal to fx, like it's
Yes, yeah, exactly.
satisfied.
Exactly.
And then this term you fill in, or like you fill it in a place where it has the type that's above, like eq something fx fy. And the type checker tells you it's the same, and this proves that fx is yx or fy. Because the
Yes.
type checker says okay to fill in the thing where they're the same and the place where they're not the same. So
Yes, exactly.
The way to understand this, there is no other instance of EQ type than ref. But ref can only be constructed for terms that have, for equal terms such that the first argument of equal and the second are the same term. Which proves equality. And symmetry as well. Can I show you an example?
yeah, sure, but that seems backwards to me.
Really?
I think it seems forwards. I guess that's a matter of perspective. So the example of, I'm sorry, I don't have any. The example, maybe the notation is hard here, but that's the example I took from.
Oh, do you want a whiteboard? Yes.
Is that okay for you?
Very true. Yeah.
So the example from Idris, modulo mistakes I make,
is. So I took that from Egypt. Can I just?
Yeah. Feel free.
So the example of definition of equal in Idris is that equal is a type like this, A, B type. Okay. So it's a type which it's a type constructor really, which has two arguments. All right. And now its only instance. I'm not sure if that's the right syntax as well or something like this. Is refl defined as equal. Okay. So the only instance of equal type exists when its both arguments are equal. And thus, if you write refl, because that's the only instance, that's the only constructor we have. If you write a refl 5,
Yeah, you can put anything else there.
yeah. Sorry, I guess I got that wrong. It's. Oh yeah, I know where I got it wrong. It's like. Can I check it actually?
Oh, sure.
Because I'm missing one piece here. Sorry.
Grab the laptop.
Oh yeah, okay. Yeah, I can't because. Okay, it's defined like this. Sorry, the equal sign that led me astray. They define it like this. Equal sign has a definition of this, and then refl is x equal x. All right. I write in one second. So refl is x equal x, where equal is defined here. So the only instance of equality is refl type, refl. What? How do I call it? Data.
Data constructor. Yeah.
Yeah, data constructor. That's the only instance of equality, but it can only be constructed if both arguments are the same. Right? Because there is no other way. They need to evaluate to the same thing. So you can write 2 plus 2 equals 4, and the answer from the interpreter would be refl 4, I guess, right? Because it evaluates it fully. You can write 5 equals 5, and the answer would be refl 5 after the computation, after the type checking. But if you write 5 equals 6, then there is no data constructor that can be applied here, and that would be a compilation error. Simply. Okay? But when you write 2 plus 2 equals 4, then after the evaluation, it evaluates to refl 4, which proves that the equality exists.
Thank you. Thank you.
I'm sorry for interrupting. But
No.
I find the Idris definition a bit easier.
That's yeah.
Maybe I didn't convey it very convincingly, but I found that definition found in Idris a bit more intuitive, I would say.
Yes. No, I agree. I agree.
I try to explain it.
It's a good point.
I understand it to you.
When you want to prove symmetry, you just swap the positions.
Yes. Yes, exactly.
Construct the same.
Exactly. Yeah, the same term, and it's still valid. And it's valid because this expression type checks. So maybe, okay, and I'm gonna just speculate here wildly, but maybe you can imagine a type system where you can't have commutativity for some reason, and then it wouldn't type check, if that makes sense. And since it wouldn't type check this operation, then you wouldn't be able to prove reflexivity. But since we are able to just kind of do it, then that's kind of how we prove it, if that makes sense. I don't know if you have a type system without commutativity. I don't know if that makes any sense.
Where we can use the symmetry.
Yes. Or symmetry? I'm not sure if... so one proof we've got here is... let's see. So... this proof is equal, not, and then plus k1, 0, and k1 are equal. So if you add 0 to k1, it's the same thing as k1. And then, this proposition, PP or proposition, and you need to construct a term of this proposition, and that would be the REFL term. So in this case, we have first we construct the case for 0. So you do 0 plus n is n, and then you have REFL net of type for all n natural, you get equal not plus 0 equals nn. And the reason there's nothing there is because plus 0, 1, n evaluates automatically to n. Because of how we defined it. It's like, because you remember how our, if there's a computation type, they get simplified. So the type of this is gonna automatically become n, and so because of this, we know that the equality will hold. On the other hand, this is not the case for this one, where you have plus n 0 equals n, because the pattern matching is happening on the left argument. So with the right argument, we need to use an inductive case where we start with the argument being 0, and then we use the Leibniz rule to build up this more complicated thing, where essentially you're adding, you use Leibniz function to add the successor, and you kind of keep doing that. Again, this is like much clearer with like a more higher level language. But yeah, essentially, yeah, that's what.
We are not using this sim function.
Yeah, I'm wondering if you could replace that with the sim function and prove that this way. Yeah, so instead, I guess that would be a good application of it, is to, instead of this more complicated way of proving it, we just apply the symmetry function, and we say that we've proven the case where plus 0, 1 equals n, and then apply the symmetry and prove that the reverse is true. And I think, you know, something like Idris, they would have automated rewriting for those cases. So you could easily do that.
So this symmetry, is this part of the class, or we define this later for what we want?
Is the symmetry part of the plus? Oh, no, so you have to prove it separately. So you'd have to do a proof that equal plus not so.
This symmetry of quality, not the symmetry of arguments of any function.
Yes, exactly, yes. So prove that a plus b is equal b plus a, and if you've proven that, then once you can, as a special case, you can apply it to prove, apply it there. So it kind of shows you how you can structure proofs and start. Yes, that's a good exercise as well. And then ultimately, yeah, we're using kind of constructing it part by part and saying that this proves PP. Yeah, that's kind of the thing. Any more questions? What do you guys have? I hope that makes sense despite the very low level syntax. I hope that wasn't too obfuscated. Cool. Cool, well, thank you very much for listening.